We are now at part 4 of lecture 18 on clustering, and in this video I would like to now look at a more practical issue when applying probabilistic models, in particular Gaussian mixture models, and that is how it generalizes and its tendencies to overfit and underfit the data. And I would like to contrast the behavior of Gaussian mixture models to k-means, and the result will be an improved way of detecting overfitting, which is applicable for probabilistic models like Gaussian mixture models, but that doesn't work with non-probabilistic models. And it's going to be an argument for why probabilistic models are particularly interesting in unsupervised learning. So recall that we are in unsupervised learning, where we have a probability distribution that is the data distribution, and our data set only consists of attributes. There's no labels, and it comes from the data distribution. We worked with the following type of probabilistic model called Gaussian mixture models, in which we have unobserved components, which we're going to infer from data. We have a set of variables z, which choose an index for each point, and then given that we have chosen an index, by the way, these indices have probabilities that are denoted by phi. Given that we have chosen an index, then we say that x is sampled from a normal distribution belonging to this that's associated with this index, and that has parameters mu k and sigma k. This is a generative story that we postulate for how that describes how the data was generated, and then we infer the best parameters given that given the data that we observe. So recall that in machine learning, a really important concept is generalization. This unsupervised model, we fit it on a data set, but we're interested about whether it has learned properties that are useful beyond just this training data set. And if we have new data, will this new data have the same structure that we have learned on our training set? And I would like to now talk about how generalization applies here in the context of Gaussian mixture models. And for this, I'm going to create a synthetic data set. And this is the same synthetic data set that we worked with in our earlier discussion of k-means. I'm generating this data set from scikit-learn using this function, and this basically creates a mixture of, it creates points that do actually come from a Gaussian mixture model, which has 4 components. This is a visualization of the points. As you can see, they don't have labels, but in fact, if we were to put the labels on this figure, we would have the following configuration. So here we have a yellow cluster, a green cluster, a purple cluster, and a blue cluster. But this is the only time when we're going to, well, in fact, we will only use these labels for visualization. They will never be used for training in any of the of the slides that you're going to see. But this just shows you that the actual data is a mixture of Gaussians. I have generated data from a mixture of Gaussians, and now I'm going to discard the labels. I will forget where it came from, and I will try to learn a brand new mixture of Gaussians on this data set, and we're going to see if it recovers this structure. And also, in addition to what I did in my video on k-means, I'm also now going to keep 50 points as a separate holdout set. So this here is a different set of points. There's 50 of them, and I'm going to hold them as a separate set, and they will not be used for training at all. So let's look at what happens if we train a small Gaussian mixture model. If our Gaussian mixture model is too small, if it doesn't have enough components, then we're not going to learn the true structure here, which has 4 components. For example, if I fit a Gaussian mixture model with 2 components on this data set, by the way, in scikit-learn, the way this is done is we use the Gaussian mixture class that's part of the mixture package, and we simply specify the number of components, and then we fit it to our data set. We only fit it to the x's. Again, there are no y's that are used here. And we can visualize its performance here. or we can visualize the results here. Similarly to what we did with k-means, I'm denoting the centers of the clusters as these red points, and it has identified them and it has placed them in interesting locations, but still this is not great because we don't recover the true structure of the data, which has 4 components. Similarly to how we did with k-means, we can measure the value of our objective function on our training set, and now I'm also going to measure it on the holdout set. And in this case, they are relatively similar. And now, of course, we're clearly underfitting, so let's increase the number of clusters here and see what happens. As we increase the number of clusters, well, here we have 4 of them, and they actually recover the true structure in our data set. But now I can further increase this. I can have 10 of them, and here I can have 20 of them. And you can see here that we are no longer fitting the true structure, we're starting to fit noise. So here there's a small number of points that are by themselves, and so these 2 points here, it thinks that these are a separate cluster, it thinks that these 3 points or 4 points here are a separate cluster, and so it's really trying to fit noise. But it is a better fit to our data. Here our training log likelihood, it improves from, it used to be 4, now it's 3.89, now it becomes 3.65, 2.92. So we achieve a lower value for our objective function. We fit the data better, which is good, but of course we're fitting noise here. However, what's interesting is that if I also measure the log likelihood on the holdout set, the log likelihood on the holdout set actually gets worse as we add more data, as we add more clusters. And this is interesting. So this instance here is a form of overfitting, which again means that we're fitting noise as opposed to the true signal, which has 4 components. And we can take this to the extreme, and we can fit data with 50 components on our data set. So we have about 150 points, and we have 150 components, so clearly we're able to fit the data super well. And the log likelihood that we have is the highest number that we've seen yet. It equals 1.58. This is the highest number. Before it used to be, with 4 components, it's -3, and now we've reached 1.58 for the log likelihood. However, this is clearly fitting noise. Here we're just fitting a cluster for these 2 points. But if we look at the holdout set, and then on the holdout set, we no longer have performance that is that good. Here we actually have significantly worse log likelihood. Our likelihood here is very bad. It is -28. And the reason this happens is that these points, these clusters, they no longer describe the data well on the holdout set. They describe the data really well on this set, right? So these 2 points are likely to have come from this cluster. Here, this data is consistent with a Gaussian mixture of 50 components. But the holdout set is no longer consistent with this mixture, with this Gaussian mixture of 50 components. For example, here we have points which are by themselves. We have centers. We have Gaussians that are by themselves in a region with no points, which shouldn't happen. And we also have points which don't belong to any Gaussian at all. So this point is not near any of the clusters, and it's very unlikely to see this point from any of our data. And similarly, these points as well, they are not likely to have been generated by this distribution. And so therefore, its log likelihood is very bad. It is very small. And here we're able to correctly detect that we have not fit the data well, and that we have overfit our training data, and we see this both visually in that this holdout data doesn't seem to come from this distribution, and we can also measure it numerically by evaluating its log likelihood. So more generally, this is a very important and very interesting observation. In probabilistic models, we can often use the log likelihood on a holdout set as a measure of overfitting. So in probabilistic unsupervised learning models, we have an objective that can be used to detect overfitting versus underfitting by comparing performance between a training and a holdout set. And it's possible that our model will have good training accuracy. Its training likelihood will be good. It will explain the training data well, but we can then see whether it explains a completely different set of holdout data. And if it has really overfit the training data, it will not explain the holdout data well. To see this, consider the following plot. Here I'm fitting Gaussian mixture models with a number of clusters that ranges from 1 to 25, and I measure the log likelihood on the training set and the log likelihood on the holdout set. Here I'm using negative log likelihood, so lower means better, and on the training set we go from basically as we increase the number of clusters, our performance keeps improving, but on the holdout set, our performance plateaus at around 3 or 4, and here we no longer see any improvement, and then after a while we're clearly overfitting and our performance becomes much worse. And so here we clearly see that this is the kind of curve that we would expect with unsupervised learning, and we can get some of this in an unsupervised learning regime as well if we use a probabilistic model. And that's a very useful feature of probabilistic model, and it is an important reason why they're interesting and really great benefit, and I am personally a big fan of probabilistic models. Now, I also want to give you a warning. This is not a foolproof solution. So it doesn't work in every possible regime. It provides a lot of useful hints for detecting overfitting, but it's not a bulletproof solution, and it is not as reliable as measuring accuracy in supervised learning. Just to give you an example, here in this particular regime, even as we reach 8 or 9 clusters, this performance is still not good. We do not see a big increase in our negative log likelihood. It is relatively small compared to the increases that we see later. So here we're off we're still quite off in terms of the optimal K, but we don't have a big increase in the log likelihood. We could, however, detect this, that here we seem to start with overfit here because the curve are no longer parallel starting at 4, but this is not obvious to see. And also there are some paradoxical behaviors in that if we had significantly more data, then this flat region of the curve would last for much, much longer, and it would make it even more difficult to detect these kinds of overfitting problems. So again, even though the log likelihood can help us detect overfitting, it is a useful technique, but it's not entirely bulletproof, and you should play with it. You can play with the example in the code in this example to better understand its limitations. So in other words, to summarize, generalization is important for supervised and unsupervised learning, and in probabilistic models like Gaussian mixture models, we can detect it by comparing the log likelihood over the holdout set and the training data. And if we need to reduce overfitting, the same techniques that we have seen earlier hold. We can, for example, reduce the number of components in the Gaussian mixture model.